Hey guys, welcome back to General Chemistry. Today we're going to dive into a Hess's Law example. In the previous video, we talked about some skills to help us with Hess's Law. So first we're going to use those skills for sure. And we're going to learn one more set of skills, and then we can dive into a full-blown Hess's Law problem. But before we do any of that, let's define what Hess's Law is. So if a reaction is carried out in a series of steps, the enthalpy change for the overall reaction will be the sum of the enthalpy changes for each individual step. That's a lot. That's a pretty heavy statement. So let's first talk about a couple of terminology pieces here. So we've got overall reaction, that's something we've never heard before, and we've got series of steps. Okay. The overall reaction is what we've traditionally posted on our board, right? So traditionally we would have some sort of chemical equation. Maybe it's maybe it's something like this. Okay. So these reactions that we posted on our board have all been the overall reaction. But as it turns out, that might be an oversimplification. So actually, when we have these chemical reactions, very often they happen in a series of steps. So they're carried out in a series of steps. So it may not be that hydrogen and oxygen perfectly react to produce water. It may be that one molecule of hydrogen and oxygen react first. And then later on, along comes the other molecule of hydrogen and shake things up. And then eventually we get our product of water. Okay? So that's the first new kind of concept here is reactions typically happen in a series of steps. Okay? That's the hard part. The easy part of Hess's law is if we know, so if we have, let's say, step 1, step 2, if we know the enthalpy change associated with each of those steps, what Hess's law tells us is if I were to add up the enthalpy changes associated with each of those steps, I can determine the enthalpy change for the overall reaction. Okay, so that's what Hess's law is. Enthalpy from step 1, enthalpy from step 2, add those together, I can determine the enthalpy for the overall reaction. Well, adding and subtracting numbers is easy. We've been doing that since first grade, right? The hard part is adding together chemical reactions. So how do I add together step 1 with step 2 to determine the overall enthalpy change or the overall reaction? And that's going to be the more challenging part. That's going to be the step that we have to take a little bit of time to get used to. Very busy graphic, so I want to go ahead and stair-step you through this. So our series of steps. So this blue arrow right here represents step 1. Red arrow over here represents step 2. Okay. So step 1 in this reaction, our reactants are going to be A plus 2B. So that's my reactants, that's where my reaction arrow starts. And the product, the end, what it's going to produce is going to be the molecule C. So that is step 1, and there's an enthalpy associated with that step. Okay, let's just throw a number in here. Let's say that that's 95 kilojoules. All right, now we have, you know what, I should do that one in blue. Let me erase that and do that in blue to match our graphic here. So A plus 2B produces C, and the enthalpy change associated with this, let's say, is 95 kilojoules. Okay. Step 2. So step 2 is actually going to start from here, right? So for step 2, our reactant is C, and then when we finish our reaction, our product is 2D. And there's also an enthalpy associated with that reaction. This is a big negative, so let's call this negative 195 kilojoules. Okay. So according to Hess's law, if I want to determine the enthalpy change for the overall reaction, I simply add these two numbers together. So 95 plus negative 195 tells me that the enthalpy for the overall reaction is negative 100 kilojoules. Like I said, guys, that's the easy part. We've been adding and subtracting numbers forever. Okay? The hard part for this one is, well, what's the overall reaction, right? So how do I add together chemical reactions to determine the overall reaction? Like, what does that look like? Okay. So here we see our series of steps. This is step 1. This is step 2. The first thing that we're going to have to identify is something called an intermediate. So an intermediate is something that's created in one step and then immediately consumed in the next step. So as soon as I make a big old pile of this molecule C, that molecule C is going to begin to break down into 2 molecules of D. So this intermediate will not be included in our overall reaction. For example, if I were to take A and 2B and put them into a beaker, I walked away from the chemical reaction and I came back 2 days later, I would never see that molecule C. I would simply see what my product is. Okay? So C is an intermediate. It's produced and then immediately consumed. Another way to identify these is they're on opposite sides of the reaction arrow. So here it's a reactant, here it's a product, here it's a reactant. So those are on opposite sides of the arrow, so that's another indication that it's an intermediate. Once we've identified our intermediates, we then just keep everything that we have left, and we keep it on the side of the reaction arrow that it's on. So from step 1, I still have A plus 2B. Then I have my reaction arrow. C is gone, so we're not going to include that. And then on the product side over here, C is gone, so we're not going to include that. And all I have left is 2D. Okay? And this, my friends, is the overall reaction. So that's the hard part, is adding together the steps to get to the overall reaction. Once I know what the overall reaction is, then I just simply add up the enthalpy numbers, and that gives me the enthalpy of my overall. That's the easy part. So let's look at an example. If this reaction on the board is carried out in, if the reactions that you see on the board are the series of steps. So this is step 1, this is step 2. Let's see if we can determine what the overall reaction might be. So this is our first attempt at adding chemical reactions together. Okay. First thing to notice, I wouldn't typically write it like this, but our reaction arrow is kind of off-centered here. So I like to just kind of cut off our reactions, products, and reactants so we know what's what. Okay. So let's see if we can identify any intermediates. Well, here I see carbon monoxide is produced, and then in the very next step, it's consumed. So that's an intermediate. Here I see oxygen, half a mole of oxygen is produced, and then a half a mole of oxygen is consumed. That's an intermediate. Okay. I don't think I see any more intermediates. So now we just keep everything that we have left, and we just kind of carry it down. So on the reactant side, I have CH4 plus 2O2. That's my reactant side. And on the product side, I've got from step 1, I have 2 molecules of water that formed. And from step 2, I have carbon dioxide that formed. Okay. So in this case, we looked at our series of steps, and now we've gotten to our overall reaction. Okay. If I were to give you the enthalpies for each of those steps, now that we've determined the overall reaction, now that we've determined the enthalpies for each step, finding the enthalpy for the overall reaction according to Hess's law is going to be just taking negative 283 plus negative 607 kilojoules. So the enthalpy for our overall reaction would be negative 890 kilojoules. So that's the basics of Hess's law. The problem is the series of steps may not always be experimentally determined or experimentally done in the correct order. Yeah? So both of these reactions happen to be exothermic. And so those would be pretty easy steps for us to gauge. But what if one of these steps was endothermic? Well, it's really hard for us to, in a lab, perform an endothermic reaction and be able to measure exactly how much energy went into the system. So if I'm putting it on a hot plate, well, how do I know how much energy went into the system? And was there any excess that went in there that I shouldn't think about? So endothermic reactions are very hard for us to monitor, but exothermic are really easy. So sometimes when we see our series of steps, they aren't necessarily in the order that we need them to be in. So here's what a full-blown Hess's problem is going to look like. This is the overall reaction. And I want to know what is the change in enthalpy for that overall reaction. Below are 2 steps. These are the 2 steps that I experimented, or the procedure I did in the lab, and I was able to experimentally determine the enthalpies for each of these steps. Now, I need to rearrange and manipulate these 2 steps so that when I add them together, they equal the overall reaction. Okay? So let me say that again. I need to manipulate these 2 steps so that when I add them together, they are going to equal the overall reaction. Okay? There's a number of ways to do these problems. If you like Sudoku puzzles, this is going to be fun for you. There's no right or wrong place to start, and some students cue it on different things, right? So there's going to be a number of different ways to solve these problems. Okay. So if I want to add these 2 reactions together to equal my overall reaction, let me start to look at some things that are going on. Well, one of the first things I see is that sulfur trioxide is my product. And right now, if I look at this series of steps, I see sulfur trioxide as a reactant. So if I just simply add these 2 steps together the way that they're written, sulfur trioxide is going to be on the complete wrong side of the equation. So probably one of the manipulations I'm going to have to do is I'm going to have to flip this second reaction. I want sulfur trioxide on the product side. So I'm going to flip this over so that sulfur trioxide is the product. And that means that sulfur dioxide and oxygen become the reactants. I'm going to cross that out just so we don't look at it anymore. Okay. Well, when I manipulate a equation, and we talked about this a couple videos ago, when I manipulate an equation, the enthalpy change is going to have to reflect that manipulation. So for this one, I reversed the reaction. I flipped it. So what happens to this sign of enthalpy? Yeah, it also flips. So if the forward reaction was a negative enthalpy, the reverse reaction is going to be a positive. All right. So that was a pretty significant change, yeah. Let's see if anything else jumps off the paper. Okay, so I've got my sulfur trioxide in the right spot. And I've got two of them, so that's good. I need two sulfur trioxides, and it's a product. So that's kind of in the right spot. Okay. Let's come over here and look at my reactants. So sulfur is a reactant. Yeah, I need it to be a reactant. But how many sulfurs do I need? Yeah, my overall reaction has 2, but the step only has 1. So I'm probably going to have to multiply this step by a coefficient of 2, right? I need that to have 2. Okay. So I'm going to rewrite that down here. So 2 sulfurs plus 2 oxygens are going to give me 2 sulfur dioxides. Okay, so I just distributed that 2 to each of my molecules. I don't want to look at that anymore. Okay. Well, anytime I manipulate a chemical reaction, the enthalpy is going to have to be reflecting that change. So if I multiplied by a coefficient of 2, I also have to multiply the enthalpy by 2. Okay. So the enthalpy change for the reaction at the bottom is negative 297 times 2. Okay. All right, y'all, I've made 2 fairly significant manipulations. I have reversed one of the reactions. I have multiplied one of the reactions by 2. Now let's add these 2 together and see if we can get to our overall reaction. Okay. So the last step is going to be to identify and eliminate any intermediates. So 2 ways you could do this. You could look at like opposite sides of the reaction arrow. That would be fine. Or you can look for something that is not in the overall reaction. Since you have the overall reaction, you can kind of use that as like, oh, I don't see any of that in there. It must have been eliminated. So my intermediates here is the sulfur dioxide. Okay. So sulfur dioxide is on opposite sides of the reaction arrow. So here it's a product, here it's a reactant. So it's on opposite sides of the reaction arrow. So that's going to be an intermediate. I also don't see it in my overall reaction, so that's another indication that it must be an intermediate. Let me ask you about this one. Is oxygen considered an intermediate? It is not. Why would the oxygen, even though it's on both of the reactions, why would it not be considered an intermediate? Because it's on the same side of the reaction arrow, right? Reactant, reactant, that's not going to cancel out, right? That's actually going to add together. So because those are on the same side of the reaction arrow, it is not considered an intermediate. All right, so let's add these 2 equations together and see if they're our overall reaction. So from step 1, I have an oxygen. From step 2, I have 2 more oxygens and 2 sulfurs. Looking at my products, from step 1, I have SO3. From step 2, I have nothing. Okay. So does this look like our overall reaction? Almost. We've got 2 sulfurs, 2 sulfurs, 2 sulfur trioxides, 2 sulfur trioxides. The only thing I don't see on there is the 3 oxygens. But if I clean this up right here, so 1 mole of oxygen plus 2 moles of oxygen Well, that's going to clean up into 3 moles of oxygen. So now we have our overall reaction. So the whole purpose of this exercise was to determine the enthalpy of the overall reaction. As long as you keep track of the changes for the enthalpies as you work through this problem, as long as you keep track of the enthalpy changes, the last step is very easy. You just add them together. Okay? So to determine the enthalpy change for this overall reaction, we're going to take 198 plus negative 594. So the enthalpy change for this reaction is 396 kilojoules. So that is a full-blown Hess's problem, and they're difficult, they're tough. So I highly recommend that you guys seek out Hess Law problems and make sure you practice these until they become a little bit easier for you. I hope you guys found this helpful.